This section explains the Llama model and code implementation. Let's first look at the Llama model overview. By combining RMS norm, rotary embeddings, multi-head self-attention with relative positional encoding, and SwiGLU-based MLPs, Llama introduces a highly efficient transformer architecture that improves both training stability and model performance. The key innovations, such as rotary embeddings, allow the model to capture relative positional information, which is critical for many NLP tasks. Root mean square normalization. RMS norm is a normalization technique that works by normalizing the input activations using their root mean square value instead of their mean and variance. It was introduced as an alternative to layer norm in some transformer models. Formula for RMS norm as follows. Steps in RMS norm. 1. Compute RMS. The RMS value is computed along the last dimension of the tensor, usually the feature dimension. 2. Normalization. Normalize each element by dividing by the RMS. 3. Scaling. Scale the normalized values by a learnable parameter weight. The final output as follows. Rotary Positional Embeddings. Rotary positional embeddings are a way of encoding relative positions of tokens in a sequence. The key idea is to use sinusoidal functions that allow the model to encode positions efficiently, and these embeddings can be rotated to account for relative position information. Formula for rotary embeddings. Given a sequence length L and an embedding dimension D, the rotary position embeddings are constructed by T is the position in the sequence, I is the index of the embedding dimension. The frequency decays exponentially with the dimension. In the forward pass, we apply these embeddings to the query and key vectors in the attention mechanism. For a given query and key, the rotary embedding is applied as follows. Q is the query tensor. Q roll is the query tensor shifted by 1, to account for relative positions. Theta represents the angular frequency calculated above. This allows the model to attend to relative positions by modulating the query and key tensors during the attention calculation. Multi-head attention with rotary embeddings. In Llama, the attention mechanism is modified by incorporating the rotary embeddings to encode relative positions. Below is the mathematical formulation for the attention mechanism, including the rotary embeddings. 1. Query, key, and value projections. The input sequence X, where B is batch size, L is sequence length, and H is hidden size, is projected into queries Q, keys K, and values V. 2. Reshaping for multi-head attention. The queries, keys, and values are reshaped into multiple heads. For example, if there are H equal 512 hidden units and N equal 8 heads. 3. Rotary Positional Embeddings application. Rotary embeddings are applied to the query and key tensors using cosine and sine embeddings. The queries and keys are rotated relative to each other by the embeddings, where theta represents the pre-computed rotary embeddings for the sequence positions. 4. Attention scores. Calculation. The attention scores are calculated by taking the dot product of the query and key vectors. This produces a matrix of shape, B, N, L, L, representing the attention scores between each pair of tokens in the sequence. 5. Softmax and output calculation. The attention scores are passed through a softmax to get the attention weights. Finally, the output is computed as follows. The resulting tensor is then reshaped back to the original hidden size H and passed through the output projection. Feed-forward network. Llama uses a modified feed-forward network that includes SwiGLU activation, which is a variant of GLU, gated linear unit. This network consists of 3 linear layers. 1. Linear projections. W1, W2 are learned weight matrices. 2. SwiGLU activation. The activation function is a combination of a gating mechanism and a linear transformation. 3. Output. The final output of the feed-forward network is as follows. Now we implement the Llama code. RMS norm class. Rotary Embedding class. Llama Attention class. Llama MLP class. Llama Decoder layer class. Llama Model class. Testing the Llama.